I'm working usually on star formation, and I'm giving talks usually to astronomers. This time, I decided to change following the advice of Jerome and being very pedagogical, as he said. So this talk is for data scientists. So astronomers, please, you can leave the room. You all know my shit. This is not for you. So the idea is we will talk about fibers in molecular clouds, what they are, how we identify them. I spent some time more on the methods than on some of the results that we can discuss if you want later. But of course, I need to set the scene. Sorry that you don't see the entire screen. So what we are trying to do is to understand how stars form in molecular clouds. And this is a long-standing problem, and we learned a lot about these things in the last years. So we know that a low-mass star usually forms in what is called a dense core. So it's a sphere of gas that eventually collapses under its own gravity. And these dense cores are usually not alone, and they are connected by emission that extend over several parsecs in length in molecular clouds, and we call these structures filaments because they are elongated. And they permeate molecular clouds and actually dominate some of the structure of these objects. So this is known already for almost a century, or more than a century actually, and this is part of the hierarchical structure of the ISM. So can we remove this somehow? No. Okay, well, so we're interested and we will focus on the kinematics of these objects. And this is because we know, and this is again also not that we said not anything new, we know that molecular clouds are supersonic, so they have large turbulent motions at large scales, while okay, so now, yeah, better. While we know that dense cores, so before you form a star, the turbulence is dissipated. And somehow something happens in between that needs to get rid of this turbulence. So this is where we focus. So, oops. So the idea here is whether we can explore what is the role of filaments in this hierarchy. So how filaments then at the end fragment and form stars, and whether their properties change between different environments. Yeah, I think you can hide that, right? Hide names, hide floating medium control. Yeah, that one. Yeah, perfect. Much better. Thanks. So, oops, no. So how do we do that? So in my case, I'm studying emission lines from molecules, molecular emission. That you see here one typical example of a very nicely behaved Gaussian profile. And what we want is to make sense of the profiles of these lines, and for that we use the simplest approach, which is in our case, and is not the only approach. You feed Gaussians to this distribution. It's because each parcel of gas emits over a range of frequencies, a range of velocities, and you need to capture the entire physics by that. We do this by feeding Gaussians, and that allows you to quantize and parameterize the entire emission, given the peak intensity, the full width maximum, the shift of the centroid, and the integrated intensity. So what I'm going to talk about is on the kinematics that you can extract from the analysis of the widths and the velocity shifts of these lines. Why do we study molecular lines in general? I mean, you have now a full project only on that. It's because this apparently simple profile encodes the physics of the ISM. It's a complex correlation between different parameters, but if you basically try to explain the shape of this Gaussian line, you can basically go to the radial transfer equation and then derive many interesting properties, like the excitation of the line, the background radiation, the intrinsic properties of the molecule. You can do astrochemistry with that. You can compare different things. And you can do kinematics. This is what we are doing here. So our goal, and I did this with some of the people here in the room, we try to understand this process of turbulent dissipation and turbulent structure in molecular clouds using or analyzing the kinematics of different molecular tracers. This is because each of these molecular tracers tell you a slightly different story due to the chemical and excitation conditions of these molecules. And I will be talking about two tracers here, basically CO, which is a tracer of a bit more diffuse gas, and some nitrogen molecule like N2H+, that is a tracer of a high-density material. The reason for that is because of, again, chemistry. I don't have time to explain that. Just please believe this. I'm sure people will talk about it later. So these are our tools and approach. what we are trying to do is to solve a very complex problem. So we want to understand how molecular clouds behave. What is the physics of a molecular cloud? But each parcel of the gas in the molecular cloud has, or is the physics defined in 6 dimensions. You have 3 spatial dimensions from our rest frame, what it is, x, y, and z. And each of these particles moves also in a 3-dimensional way with 3 velocity components. So this is the true physics that we want to infer, right? This is called the PPP-BBB space, the true physical space of our molecular clouds. Unfortunately, we as astronomers do not have access to these 6 components in general. I mean, some cases we do, but in very rare cases we can access the full 6D dimensions. And in practice, depending on what you are observing, if you observe continuum, you basically collapse your parameter space into 2 dimensions. You can see only things in projection of the sky, so how the sky emits in different locations, but you don't have any other information. And in our case, if you use molecular lines, you can get access to an extra dimension, the velocity dimension along the line of sight, the Doppler shift of your molecules along the line of sight, and that gives you access to a slightly peculiar phase space, which is, I call it 2 + 1 dimension. So 2 spatial dimensions, 1 velocity dimension, PPV space. This is great. I mean, we learn a lot, and I will show you what we did. But this comes with several caveats when we interpret our measurements and our analysis. Remember, 2 spatial dimensions, 1 velocity dimension. We call it, you can do x, y, z, or x, y velocity, so local standard of rest. So depending on how you want to do that. But again, remember that we want to interpret a 6-dimensional space by 2 + 1 dimensional measurements. And this is a tricky thing to do. So what we did, actually years ago, back on my PhD thesis, we were studying one of these filaments that form stars, and we thought that this is a prototype of these type of structures. This is called the Barnard 213 filament. This is the torus molecular cloud. This is a very long filament, 10 parsec long structure, very nicely defined as an elongated thing, 10 parsec long. So a massive object forming on the order of 40 stars. So this has been a prime target, for instance, for Herschel, and I'm sure that the next speaker, Philippe, will talk a lot about that. So if you observe this region in continuum, again, access to the 2D PP dimension, you see again this filament, and you can try to fit a profile and do things like this. So in principle, if you look at this 2D space, it looks a simple structure. We studied the same region, this is just a part of our data, in molecular lines. And again, now we have access to this 3rd dimension that is velocity. And if you see different spectra that you have here, sometimes you have 1 velocity component, right? But sometimes you have 2 velocity components that start shifting in velocity depending on what you look at. The intensity changes up and down. Sometimes you have 3, sometimes you have 4, and you have up to 5 different velocity components along the line of sight. This is in CO. This is the blue spectrum that you see here. And if you look at the dense gas in N2H+, sometimes it appears in one of the 2 components. Never in between, never outside, either one or the other. Sometimes we see hints of a secondary peak, even another one. So something is happening there that what looks like simple in 2D space, position space, is much more complex in position velocity space. So we wanted to make sense of that. So what we did, and I will not, unfortunately, spend so much time on that, but I wanted to just mention this because it's part of the theme of the meeting. So we tried to decompose our cubes with Gaussians. And we did that. We have 25,000 spectra, and we tried to decompose this as better as we could, selecting the number of components that we have in each pixel, and then try to fit the corresponding number of components. So this is the workflow that we have. The idea is to extract all so parameterize basically the cube. We don't want to play with the cube by itself. We want to parameterize the cube and then work with that. So we want to the line profiles, the line widths, the velocity of the lines, and so on. And we want to do it with thousands of spectra. So we managed to kind of automatize part of the process. This is a bit trying to be smarter and then try to average spectra and get high signal to noise spectra to see how many components we have, which is the critical step of the process. Unfortunately, we only managed to make it semi-supervised. So at some point, you see the eye there. This is a monkey looking at how many components you have there. The monkey is usually me, checking how many components you have there. But based on this decision, you can try to kind of fastly cover your cube and then extract your parameters from the spectra. And unfortunately, and you will see that later, this is time consuming and something that needs to be, could be heavily improved. There are other softwares in the market, but if you have ideas, that would be a great thing to do. So anyway, so imagine now that we are with the data, that we managed to decompose the cubes into these Gaussian, and now we have information per pixel per component. So pixels with more components, we have more than one data in our analysis, and some that have none, we have 0, and so on and so forth. So what we did is to put the results of this analysis in this pseudo position velocity space. And what we found was something very surprising. So these are the data in a fraction of our cubes, where each of these points corresponds to the position of the spectrum and the velocity of the Gaussian that we fitted. If we have two Gaussians in the spectrum, there are 2 points here. If not, there is just one. And although we work with that, just to remember that each of these points still carries all the information of the spectrum, the peak, the width, and the intensity of the light. So what we saw directly on this data, without doing anything, is that the points are not randomly distributed. They are forming some kind of wavy structures that are continuous in this position velocity space. And the assumption that we wanted to make is that this continuity in this position velocity space corresponds to true continuity in the position velocity space, right? So how do you do that? I spent some time doing it by hand, but of course you want to make this automatic. So we created an algorithm called friends in velocity, which is, the simplest thing that you can try. So the idea is that we wanted to reconstruct this, what we call velocity-coherent structures. Velocity, so continuous in space and velocity, as you saw in the previous slide. And avoid any other prior on the structure of this, or the properties of these objects. We just want to connect them and extract them to be able to then calculate other parameters. For, again, data scientists, if you want to create an algorithm, you need to define a metric. You need to define how you are going to connect these points. And to some degree, in particular when you deal with this type of 2+1D analysis, is kind of arbitrary. So our choice, might not be the only one, is to use a friends of friends algorithm. This is a classical cosmological algorithm that you start from a point and try to look for similar points. If they are similar, you connect them, and then you keep increasing and then growing your structures until you cannot connect your points anymore, and this is another structure. To define what is connected and what is not, you need to define a linking length, so how far you are going to look for your, what is called friends. So is my friend within a certain distance? And if so, fulfill some conditions. And you need, and this is part of, again, another arbitrary choice, what is coherent? What is coherent in velocity? And in this particular case, we decided that 2 points at a distance of friends are connected if their velocity gradient between them corresponds to a certain velocity jump between them. This is, again, this is a definition. There's nothing in the physics that tells you that you can connect these 2+1D in that way. So if you have better approaches, that's another option. So how do you do that? Well, first, we need to identify the green point. This is just an example of how it will be working in theory, obviously. So if you have access to the position space and the position velocity of two structures, continuous in velocity. So the first step of this algorithm is to try to identify the high column density material, which is supposed to be connected somehow, not necessarily in an elongated shape, just connected. So we first try to identify these green points. Basically, we look around every point and we try to find if they are high density and have high density number of friends. Then we connect only these points. So let me go back. We try to connect first only the green points that are those identified in the first step, given our criterion. And in this case, we decided to go for 3 kilometers per second per parsec gradient connecting the points. The reason for that is that for the distance that we are using to find friends, you allow only jumps that are on the sonic regime. So the jump between one point and the next one within this velocity gradient and the size that we are looking at connects 2 points that are within a sonic jump. They are not supersonic connections. They are only sonic jumps. And the third step is that once you define these, basically the spines of these things, you just make them grow. And you grow in the same way, in the same manner with this friends of friends algorithm, layer by layer. So you have the spine, you grow the first layer, you try to figure out if there is another layer, and so on and so forth, until the structures cannot grow farther, and then you stop. Or some others might grow, and some others might grow from both sides and then collide at the center. This is one of the limitations of the algorithm. So, but this is a very simple approach to try to make sense of this kind of mess, kind of structure in the position velocity space. So how it works now? So going back to the real data now. So this is our raw data, the results for the Gaussian decomposition of the spectra. The cube is, by the way, much longer. It's just a small fraction of it. So this is the step one. You identify the high column density material, and of course, many of them are already connected. So this is what we wanted. Then you identify these first structures, you connect these green points, and then you define how many structures you will have. And then you make them grow until you identify as many points as possible. This is not 100% of the points. Some points will never be connected in that way, but that's the way we identify these structures. So what you can see directly in this plot is that, again, what looks like a very simple structure in position space is actually quite complex in position velocity with multiple, and multiple depends a bit on these parameters I just told you, but many of structures superposed along the line of sight. So just to look at how it looked like in space, let's go back to the part of the cube I just showed you. So the background image is the Herschel image. So the continuum image 2D. And look at, this was supposed to be a single filament, but even in Herschel, you start seeing some substructure in there. So look at this lower part that the filament seems to fork, and then there are structures in between that go in all directions. This is naturally recovered by our fibers, where we now, when we trace the spine of these structures. So and this is not imposed by the algorithm, we recover very elongated structures inside our filament. That basically are more than one. And more than one means that what looks like a monolithic object in continuum is actually what we call a bundle of fibers, so things that are intertwined, forming like a rope when you analyze in this position velocity space. What is interesting is that the line width that you saw, they are very narrow, so just few channels width, and when you analyze the kinematics and you recover them in these fibers, each of these structures is typically subsonic. So we were saying that the clouds are supersonic. We said that the cores are subsonic. In between, these fibers are already subsonic, meaning that the turbulence was dissipated during the formation of these structures. And in this case, we have 35 of these objects. There are other properties I'm not going to discuss here, but for us, that was the key to identify these fibers. These are the structures where turbulence dissipates. And when you have one of them and they are massive enough, this is, for instance, fiber 20, or a piece of the fiber 20, then you observe it in high resolution with high density tracers, and then you see the dense cores being formed inside them, and many of them containing already protostars in them. So these are the structure that sets the condition for star formation. You first dissipate the turbulence forming these little fibers that are typically a fraction of a parsec in length, and then they fragment into different cores, and this is the way you form your protostars. This was already what we concluded back in the days from the analysis of this filament. Of course, we didn't want to stop here because, this is a nice object, but it's not the only one. And actually, something very important for later discussions is that I said that we were using this 3 kilometers per second per parsec that allows this sonic connection, but this is also an arbitrary selection. Why not? Changing that. So if you change this parameter, so you do this exactly the same, but you allow bigger jumps in velocity, in this case almost twice, you make your jumps slightly supersonic, then you connect the cloud in a slightly different way. And that's interesting because instead of defining this very narrow thing, you define also structures that are long but are much bigger. And then that groups several of these fibers into what we call a bundle. So there is this hierarchy that I just mentioned at the beginning, is already imprinted in the kinematics, is already in the structure of the cloud. And you can recover this by just allowing different changes in these kinematic jumps. And you see now, instead of, there are 35 of these little fibers, and there are 9 of these bundles of fibers, so groups of fibers that share very similar properties in terms of kinematics, in terms of chemistry. What? Okay, sorry. And that will become very interesting for a later discussion. So, but again, we didn't want to stop here. We wanted to go into higher resolution. And this is also part of the future if you talk about ALMA. So we wanted to do the same analysis in the integral shape filament in Orion, another very famous filament. This one, instead of forming 40 stars, this one is forming more than 2,000 stars. This is a very big cluster at the center that is forming a lot of stars. So what we did in that case, because this region is farther away, we needed ALMA. And then we did it, and we found something I think spectacular in this sense. So this is the filament that was identified already 2010 by Johnston and collaborators, even before by John Valley. So this is in continuum on the left, again, looks like monolithic. But when you look at high resolution with ALMA in high density tracers, again, it breaks down in very little pieces. Again, resembling the same idea as we saw before, pieces that are forming these tiny little fibers. So the study of these objects require interferometers, and that brings another challenge in terms of observations. But again, this is for astronomers, so you don't care about that. So we tried to do the same analysis, and then we realized that things are getting more complicated. One of the reasons that the dynamic range of regions like Orion is huge. So you go from very low column densities to super high column densities, 2 orders of magnitude in column density. And then the simple criteria that we were using before is not enough. So we need to do something. And so we wanted to use exactly the same approach, as simple as possible, the friends of friends algorithm. But as you see on the top, if we use just one criterion, one cut in column density as we did before, we have these very big chunks that are obviously not a single thing, because you see multiple branches all over the place. So we wanted to do some kind of hierarchical analysis, and this is how we implemented this. It's not perfect, of course. I mean, there are choices that determine how well you break these things, and you can break better one thing and not that better some others. But this is what we do. We wanted to keep track of that. And the second criterion is that you can no longer identify a single velocity jump in your analysis. And this is because, this goes back to the information theory, if you have 2 lines separated in velocity, you cannot differentiate them if the velocity difference is larger than half of the width of one of the lines. So this is the Nyquist criterion. So if 2 lines are together, too close together, even if they are a bit shifted, technically they are the same within the width. So, and the width changes in these regions all over the place. So there is no way that you can set a single value to identify all. So what we did in this case is to change the global criterion by a local criterion, where at each point, at each XY position, we decide whether we connect or not points, given the width of the line locally. So how we can go to the next pixel, and they are connected if the velocity difference is below the typical half of the line width of the line. And in this way, you can reconstruct things. So these are the results of the analysis. Again, now dozens, in particular 53 individual objects inside there. Oh, okay, it will be fast. With properties that you see here that are basically the same in every single region. When you do that, you decompose your cloud, and then you have, basically, you recover the same structure in all molecular clouds. The lines are typically subsonic everywhere. So these pieces, these little pieces that we identify, are the same in every single cloud. So this is what we think. Again, these fibers are the precursors of star formation, at least for the low mass stars. We can talk about the high mass stars another time. So, but what changes, I mean, something for later, maybe we can discuss this, The width changes from region to region. I'm not going to spend more time because I want to jump to the next thing. So these are the two filaments in the same width. And what my PhD student was demonstrating later is that actually the fibers adapt their width to the local environment. So this is comparison with Herschel that I'm sure Philippe is going to talk about, typically 0.1 parsec. These things can go much smaller when you resolve them with interferometer. And this is the plot. Then a few more minutes on what is next. So how we see these objects in the big picture of star formation in the ISM. So in 2023, we decided to plot all filaments together, everything that people mention as a filament and describe as a filament in a single mass length plot. And as you can see there, basically filaments are across all scales, across all masses. And they follow a particular distribution, which is interesting. So again, it's not a cloud of points, it's a correlation of points. In this, so the definition of this and how you see these things is because, as I showed you before, we are talking about a hierarchy of structures. This is not a single type of structures, what we call filaments. They are filaments at all scales, and depending on which resolution, which scale you look at, you will see different filaments in here. And the fact that they describe a correlation is because they are connected to one another. So in this hierarchy of filaments, fibers are at the bottom of this cascade. So because you have these filaments within filaments within filaments within filaments, and this ends when turbulence dissipates, and this is how you find our fibers. So in this sense, more important than identifying a particular structure is to identify how they connect, how you correlate these different structures across scales. And what we found is that on average, all filaments follow this mass length relationship of so mass to the power of 0.5. So, which is interesting because this connects with the scaling relationship of the ISM that have been discussed already for decades in the Larson relationship, with the extra thing that we decouple the length and the width of filaments. And that gives you a different relationship for the aspect ratio of these objects. I don't have time to talk about that. But what is important is that different filaments occupy different parts of the plot. Let me go back to this. One simple idea would be that, okay, this is the correlation and that's it. So the scatter in this plot is just noise. But this is not true. And actually, when you isolate different clouds, you see that each of the clouds have a very narrow distribution in this plot. And it's because there is some physics behind these correlations that first set the slope and then set the normalization of this distribution. And here you have three different clouds, all of them with the same slope, but each of them with a slightly different normalization. And we think that this normalization is given by the accretion rates of the individual objects. This is something that we are testing here. This keeps going, so you keep accreting, keep moving to the right until your structure collapses by its own gravity and then moves out of this correlation. And we have a paper discussing this. But going back to my last two slides. So the future is not on identifying more fibers. The future is not on identifying more filaments. The future is to connect these things. So this is my personal view. So remember what I just showed you. So this is one long filament that if you put it in this mass length plot, is up there on the corner, the upper right corner, and that connects with all the structures within that. And so if you plot the bundles, these big groups of fibers, you can basically predict what they are because they follow this mass length relationship for filaments. And this is because we think the way you create these structures is by turbulent fragmentation. And this naturally connects these two things. And in the paper, we explain why this specific slope. But again, this is now one. So the pink one, the more of the roundies are the bundles. So you see all of them below this line. The pink one is now bundle number 6, which is the active one that we have here. And if you then look at the individual structures, so now we have one of these fibers, and basically it's almost on top of the thing. And then the cores in there, the cores are of this relationship. And this is because the physics changes the orientation of these slopes. And it's a very easy thing to understand. Turbulent fragmentation produces random motions and random fragments that follow this mass to the power of 0.5. If you have gravitational fragmentation, so you have a single structure and you fragment into pieces, the predicted slope is m to the power of 1. And this is what happens when you connect this structure with the course. The slope of these things change. So the future, at least from my point of view, is to now try to understand how these things connect, and basically how we quantify these things and how these things connect. It will tell us a lot about the physics in them. So as I said, this is a talk for data scientists. So these are my questions for you. There are several challenges that we need to overcome. Maybe somebody can give us some help. So we need to understand, thinking about the future, how we, instead of fitting thousands of spectra, how we fit millions of spectra in an automatic way. So not monkeys anymore. The monkey is tired already. We need to understand better this connection between the 6-dimensional space, the truth space, and the 2+1D space that we have. We need to understand the hierarchies. As I showed you, I think this is the future. And we need a new generation of algorithms that can tell us about that. With this, I finish, and I'm happy to take your questions. Maybe I can. This is more important.
Okay, so thank you very much for this very interesting and nice talk. So do we have questions for... I'll get you first name, Hacar. Alvaro.
No.
Thank you, Alvaro, for a very nice talk. I have a question about your M versus mass versus length for the filaments and fibers. You have a correlation with going as M with the square root of the length. This is equivalent to, or L going as the square root of the mass. Sorry, so that's equivalent to mass going as the square of the length, and this means there is a characteristic surface density. I mean, for a typical aspect ratio. And aren't you? My worry is that, of course, any observations have their sensitivity limit. And so they are only sensitive to a certain surface density. And for instance, the H1 filaments in brown are sensitive to much lower surface density than what you have in molecular clouds. So it's not surprising that you have different groups of structures in different parts of the diagram because they are sensitive to different surface density. And the correlation may just be due to this sensitivity limit. Aren't you concerned about this?
First of all, there's indeed a correlation. So you can draw and actually predict what is the surface density of the different filaments. And this gives you an stratified medium like this. So actually, you can start, for instance, with this. It's not exactly that, but the dashed line is the column density that you need to produce molecules. So this is one extinction in magnitude that separates the atomic filaments, which are on the left, with the molecular filaments that are on the right. So indeed, there is some column density dependence. And of course, the farther you are to the right, the higher column density you are. But you do not allow every single combination. And if you plot the results for different filaments for different column densities, they follow exactly these predictions. And the fibers are at the bottom of this cascade, which are the shortest, the highest column density, and those that are subsonic.
Yes, but my point is that it would help to plot the mass, the surface density limit of any group of observations.
We did it. I mean, I don't have the time. I didn't have the slides and the time, but we did that already here. So we have already discussions on how, because you can even predict this from this super slow. So from these scaling relationships, you can predict the expected surface density of filaments. And again, this stratifies your medium, and then that fits exactly the observations, indeed.
So when you have all of these data points together, are you able to trace for a single object, for example, or in Orion, you go to one region, you have the big filament, and then you have the fibers. Can you calculate what's the efficiency fraction from going from one scale to the next? You are we getting 10% of the mass at each level? Is it something that is more or less constant throughout regions? Because that would be more like the universal mechanism, as you mentioned. But if you get different fragmentation levels, then it would be a different.
So technically, yes. Well, I mean, I didn't calculate the number, but so we do that here. Basically, you see the, but again, at some point, it's also part of you are limited by your own choices of parameters in this sense. So here we are doing this analysis of, again, fibers, bundles, and the whole thing, right? And we plot them all here. So these are the different symbols. You see the legend there. So we are tracking all these things. So we can technically calculate this. We are missing some points. If you see, there are some fibers that are alone and they are not in bundles, and so on and so forth. The limitation of the algorithm is that it will try to expand as much as possible. So it will probably recover the same number of points that you see almost in this chart at all scales. You just distribute them. And how you distribute them is the key, more than the efficiency of that. You know what I mean? So what we don't, in this realization, we almost do that, yes, because as you saw, the algorithm first recognize the structure, then try to expand as much as possible. So it will try to maximize the number of points. We do not stop at a single condensity threshold, which is, I think, what you mean, how you transfer, how much mass goes from one condensity to the next one. It's by construction of the algorithm, not. In this sense, yes. So for instance, the mass value from so C18O is on the order of 1,000 solar masses, so diffuse gas. In N2 plus, I think it's like 70, 80. So it's a very small fraction of the gas ends up into dense cores and therefore into stars. And we need that for the star formation efficiency of molecular clouds. So if we will be much higher, the star formation efficiency will be much higher in general, and somehow it knows. So there's some selection also in how much material goes into the dense gas and into the stars. Yes, this is true.